This is the Chapter 7 third exam review video where we're going to look at exponential growth and decay, which is what we are using most of our exponential equations to represent. So some things I have in here, I'm near 31 and 32 on the review, is that all exponential functions can be written in this form, a times b to the x, where a is our starting amount, and then b either represents that we took 100% and added the rate that we were gaining by, so numbers are bigger than 1 for b if we were growing, and 1 minus r, numbers less than 1, between 0 and 1, if it represents decay. Everything is based off of how much above 1 or how much below 1, which really means how much above 100% or how much below 100% this was returning every time. So when we look at 31 and 32, we should be able to see in the expression whether or not it's exponential and if it represents growth or decay. So I'm going to give you an example one that's a little bit harder, and then you can go back and look to see what you think. And I'm going to do 0.82 to the x. And at first, my example might not look like exponential growth or decay because you're not seeing that a value in front. We taught you, though, in that unit that the a value might be hidden. It might be an a that's 1. And then 0.82 to the x is really representing that b to the x part, so therefore it is exponential. If it's exponential, then they wanted to know if it was growth or decay, and the way to tell was to look at the b value. If the b value is smaller than 1, that means it's representing less than 100%. And if I return to you less than 100%, you are decaying. Something is being lost or represents something that we did not get back everything we started from. You could pause the video then, and that, yes, by the way, was for my example, not necessarily for number 32. You could pause the video and take care of 31 and 32. On 33 then, and 34, we expect you to be able to graph exponential functions and come up with tables that represent them. So here's where calculator use becomes really important, and that's part of what you're seeing if you have that skill. So we always said you need all the parentheses that are represented in there. So I would go to my calculator on this one and multiply 2 by 1/4, and I might decimalize it, to the power of, and I'd start just by picking powers. Maybe in the middle of my table, maybe on the end. And I'd get my values. So this is going to come up to, okay. When this comes up this way, this one's going to come up 0.5. Okay, and as you work your way through the table, this is going to come up different values. After you get those values, then you're going to graph them. Identifying domain and range. Domain should be the easier one, and range you really want to think about how high or how low this graph is when it bottoms out. All exponential curves either have a steep part and then a slowdown, or they start with their slowdown and then hit a steep part. But either way, they have a base where they're approaching but not quite reaching a certain y value, and that will come into play for the range. So pause the video, finish that. Do not label your y-axis until you know how high all the table values need to go so that you can spread that graph out. 33, same idea. You want to be sure that you use the parentheses there when you pick on your table. So 1/3 times 3 to the 0. And that's going to come out 0.3 repeating, or 1/3 if your calculator is set to give us exact values. Okay, when you put 1 in there, this is going to come out 1. Okay, when you put 2 in there, this is going to come out 3. When you put the other values in, make sure that you find their values with a calculator and not just guess them off the top of your head. Then they want to know the pattern of change that's happening to the outputs. So something like as x increases by 1, then you're going to finish this statement with what y does. As x increases by 1, the y values do what? Not just the y values increase or decrease, but how they do. Do they add a certain amount each time? Do they multiply by a certain amount each time? Do they divide by a certain amount each time? What do the y values do? 35 and 36 get at that domain and range idea. So we'll do one of these, and then maybe you could go back to your own graph for the prior one and come up with domain and range. So for all exponential functions, their domain is all reals. You can use anything as the power in an exponential function. However, all exponential functions have a limited range. They flatten out somewhere. This one looks like it's flattening out as it's reaching for y equals this value right here, which is y equals 0. So it looks like it's using all the y values down here that are negative, but it's not using y values that are positive. It's only using y's that are less than 0. We don't even know for sure if it ever reaches 0. It's stretching up and getting really close to it, but it might hang out right underneath there. If the expression y less than 0 isn't comfortable, then write that in words. It's reaching y values that are all negative, less than 0. This is the stretching part of this exponential growth and decay, where we just first wanted to be able to identify whether they were growth or decay, but this is actually taking it apart and trying to describe what the growth and decay is actually doing. So in 36, I definitely see an exponential function whose initial amount is 2.5. It's that a times b to the x. Then to decide if it represents growth or decay, I need to see what this whole base would be, that b value that they're showing us they're showing us actually in this one how it's calculated. 1 subtract half. So therefore they are losing half each time. Our b value is really 0.5. And therefore that's going to represent decay in this situation. The growth or decay factor is the b value. So in our case, the growth or decay factor is 0.5. However, the growth or decay percent is how much from 1 did it lose. So 1 minus or plus the growth or decay rate. So in our case, this was a 1 minus 50%, so it was a 0.5 they subtracted, so it's a 50%. That's not the case in all of them. Usually if that number is a subtract, so let's kind of run a different scenario. If this one had been 1 minus 0.2 to the x, then our growth or decay factor would have been 0.8 because that's what that calculates to. That's what the power is on. But it's representing a 0.2 loss, and therefore our percentage of growth and decay would have been 0.2, 20% loss each time, the amount that is subtracted or added. We used these then in 38 through 40 to make an equation that represented a situation that was growing or decaying by a percentage. So when we look at one like number 40, and they're talking about decreasing, so you drink a beverage with 120 milligrams of caffeine. Each hour, the caffeine in your system decreases by 12%. How much caffeine would be in your system after 3 hours? So we know we want a model that looks like an exponential growth and decay function. But the 1 plus or 1 minus the rate that's got to go in there, and then this was usually t for time. So for our specific situation, we want our starting amount at 120 milligrams. This is definitely a loss situation, so we'll use a minus in there. This has to go in as a decimal, so 12%. Then the amount of time we're interested in our case is 3, and then you're going to go calculate that and come up with about how much caffeine would be left in your system. Finish up the rest of these.